Okay, thanks a lot. Thanks for the invitation and for the introduction. So this work I will present is based on two joint papers with Pieri Mastropietro, Slava Richkov, and Giuseppe Scola. One already published in 2021. The second, well, the preprint was out last year and should be almost close to final publication in these days. So the general high-level goal that motivates the problem I want to discuss is to understand the existence and the structure of the scale limit of statistical mechanics or QFT models at criticality, say the large distance behavior of correlations of statistical mechanics lattice systems at critical temperature, as well as the universality of the scale limit, so the robustness of the scale limit against certain classes of perturbations of the macroscopic Hamiltonian. So the route towards construction of the scale limit and its universality is at least conceptually clear, even though mathematically we're still far from a full understanding. So most people believe that the correct route is the following, or maybe these two combined routes. So first of all, if you want to understand the large distance behavior of correlations, one possible way is to say you start with a lattice system with lattice spacing 1. You start to, if you want to focus on large distance behavior, you integrate out degrees of freedom on small scales. After you did that, you rescale distances, so to bring back the system to a situation where the typical ultraviolet cutoff scale is also order 1. And then you iterate this operation. So this combination of integrating out and rescaling is what is known as the Wilsonian renormalization group map. And it is strongly believed that if you tune appropriately the temperature to the critical one, infinitely many iterations of this map converge to a fixed point theory, which describes the scale limit of your system at the critical point. So this fixed point theory is a Euclidean field theory that whenever it exists and is non-trivial is automatically scale invariant, and under reasonable hypothesis, locality hypothesis, it should also be conformal invariant. And on top of that, it's believed to satisfy certain additional structural properties such as the OP identities that I will mention in a couple of slides from now. So if you believe that this fixed point theory describing the scale limit should satisfy all these reasonable additional hypotheses, reasonable on the basis of the procedure you use to construct them, you can use an alternative method to somehow compute the correlations and possibly classify all the possible fixed points. These are the methods of conformal field theory. These are really complementary methods. So somehow the vague idea is that you try to exhibit somehow the full set of correlation functions out of certain algebraic constraints that come out of the requirement that correlations are in fact conformal invariant and satisfy these additional structural properties such as the OPs. Okay, so these two methods allow to make, the combination of these two allow to make amazing predictions about critical exponents of several models in 2 dimensions and partly also in 3 dimensions. Unfortunately, these methods don't really talk to each other. I mean, from a mathematical point of view, justifying the use of CFT methods starting from microscopic models, microscopic model and concrete algorithms such as Wilsonian RG is very hard. And this the attempt to connect these two visions is at least among the motivations to look at the problem I will present today. So before moving to a more precise description of the setting and the model, I would like to clarify a little bit one possible way of describing what solving or classifying CFTs by the CFT methods means. Okay, one possible way of describing what it means to solve a CFT is the following. So you can think of a Euclidean CFT in the dimensions as being defined by a consistent collection of conformal invariant multi-point correlation functions, which I will denote this way. So these are supposed to be the correlation function of a certain complete basis of scaling operators. These are essentially the same object that yesterday Kito Lacalle was calling the local operators. I will denote them by OI. So the requirement of conformal invariance is that under a conformal transformation, a correlation function transforms this way. So this is the transformation for scalar operators. There are similar ones for vectorial or tensorial operators. In this formula, omega x is the local dilation coefficient, and delta I is the scaling dimension of the operator OI. Okay, so this requirement is sufficient to fix the form of the 2- and 3-point function. So one can actually normalize the operator in such a way that the 2-point function is equal to 1 at distance 1. And once you normalize things this way, the 3-point function of any triplet of operators OI, OJ, OK is uniquely fixed. It has this form, so it's inversely proportional to a suitable combination of relative distances to powers that are constructed out of the scaling dimensions of the 3 operators. And the proportionality constant is a real constant that depends on the triplet, and that is called the structure constant.
Are there some squares missing in the 3-point function, or is it?
Sorry?
Are there some squares missing in the 3-point function, or is it correct?
I don't think so, but I may. Okay. I don't. Okay, I will double check later. Okay, so conformal invariance alone is not enough to fix higher point correlations. But if you additionally make the requirement that correlation functions satisfy so-called OP identities, operator product of expansion identities, then you're done. So OPs are non-trivial hierarchy of identities among correlation functions that can be stated a bit informally as follows. So within correlation functions, you can replace any pair of operators at distinct points by an infinite linear combination of scaling operators at position z. I mean, there is some relation between the position z and the position of x and y, but let not me later on that. So this is not, so the coefficients of this infinite linear combination are not really numerical coefficients. These are actually differential operators acting on these OKs. But the structure of these coefficients is completely fixed by conformal invariance and by the knowledge of the structure constants that appeared in the 3-point function. So somehow, if you assume that your set of multi-point correlations satisfies conformal invariance and OPs, then all you need to know in order to compute any multi-point correlation is the set of scaling dimensions, called sometimes the spectrum of the theory, and the set of structure constants. So if you take this perspective, solving a CFT means to somehow being able to compute the spectrum and the structure constants. Once you know that, you know how to reconstruct iteratively all possible correlation functions. So in 2 dimensions, there is a full list of solvable CFTs in these and in other related senses. In 3 dimensions, things are more complicated. There is at least a proposed strategy to compute consistent sets of scaling dimension and structural constants. The big idea is that you try to get constraints out of application of OPs in different ways. So for instance, if you have a 4-point function with operators sitting at 4 different points, you can decide to apply OPs, say, at these 2 pairs of points or these 2 pair of points. So you get the the same result a priori. But out of these two different ways of applying OPs, you get non-trivial identities among two infinite series involving structural constants and scaling dimensions. And in some cases, you can get out constraints for the scaling dimensions that allow to either compute them or resolve them within small windows. And in some cases, nowadays, this method has been used to compute certain critical exponents at a precision that is better than the best Monte Carlos. Yes?
Are you assuming unitarity to you certainly ruled out logarithms, etc.
Yeah, I think so.
From an assumption of unitarity.
Yeah. But yes, I think I implicitly did so. But moreover, I don't want really to enter this because unfortunately I won't be able to prove any of these strong statements. This is a bit like an overview to explain what are the features that typically one requires. Maybe there are additional requirements like unitarity or not, and then you get also other structures. Anyway,
can you quickly say what you mean by full list of solvable CFTs?
No, also here I want to be vague. I mean, there is a list. So, for instance, those with C smaller than 1 have been completely constructed, and there are others. Okay. Okay, there is a fairly complete list, or
in some regimes, you know.
In some regimes, exactly. The point of this overview is to clarify even more than what I did in the introductory slide, that so this axiomatic approach makes no reference to microscopic models. So this is a really axiomatic way of proceeding. So you may be able, out of this procedure, to exhibit a list of correlations, but a priori these correlations are the correlation of something, and it's unclear whether these correlations describe any concrete class of statistical mechanics models of criticality or concrete theories. I mean, everybody believes that the models you construct this way correspond to fixed point of certain classes of microscopic models, but this is typically unproven, unless for very few cases. So typically you don't know how to interpret the notion of average in the correlation functions, what's the physical meaning of these scaling operators. Of course, there are ways of matching certain solved CFTs with certain classes of microscopic models, but typically this is quite indirect, or by analogies, or by recognizing that certain scaling exponents are the same as those you computed in other ways in some models. So this is okay, so this is more concretely the motivation. We would like to say something about connections of RG fixed points and CFTs that are, or say the CFT axioms at the basis of the construction. So this problem is essentially unsolved, but for non-interacting fixed points, say Gaussian fixed points, and a few other integrable cases. So what is a possible framework to attack this problem? One possible framework, at least the one I will try to follow, is that of constructive quantum field theory. So the methods of constructive quantum field theory that originated at the end of the 60s have been used to prove existence and the validity of Osterwalder-Schrader axioms for a number of non-Gaussian Euclidean quantum field theories, starting from microscopic models. Microscopic models are, for example, lattice models of criticality, or functional integrals with appropriate short and long distance regulators that need to be removed at the end of the story. There are just a few cases in which one managed to, in this way, to construct non-trivial fixed points, and one can wonder whether one can say something about CFT axioms in this case. So, unfortunately, there are not so many cases in which one is able to control to sufficient detail non-trivial fixed points via constructive quantum field theory methods. So one example is the Laffinger liquid or master steering fixed point in 2 dimensions. So here I'm citing some colleagues who constructed this fixed point via functional integral methods and also proved the stability of the fixed point against certain perturbation of the microscopic Hamiltonian that break integrability. It must be said that within the universality class corresponding to this fixed point, there are exactly solvable models, most notably the master steering model and the Laffinger model, which have been solved with various degrees of rigor by Johnson, Kleiber, Mattis, Lieb. In any case, even the functional integral construction provides an alternative way to construct multi-point correlations, and they are the same, in fact, with appropriate correspondences as those coming from the, say, the Kleiber exact solution. So here one can check many things, Osterwalder-Schroeder axioms, even conformal invariance of correlations. But I would say that here the situation is a bit too special because thanks to the fact that there are integrable representatives in this universality class, one is able to compute exactly the form of all multi-point correlations, and so one can check directly validity of the say of the CFT axioms. This is in a sense a bit too special, so it's not the typical situation. We expect that typically we won't be able to write explicitly all possible correlation functions. So I'm extremely interested in developing methods that, at least in principle, can allow us to say something in situation where you don't have a full access. So this, for instance, in 3 dimensions is expected to be the generic situation. So one of the very few, maybe the only, I don't know, case of non-trivial fixed point, say in 3 dimensions, that has been rigorously constructed is the case of the long-range Ising model fixed point in 2 or 3 dimensions. This has been constructed in a series of works by Bridges, Mitter, Scoppola, Dessalines, Lane, and other collaborators. The theory is inspired by Wilson-Fisher fixed point of the 5-4 model in dimension 4 minus epsilon. But contrary to the Wilson-Fisher fixed point, it's something that can be rigorously given a mathematical meaning. So to date, we don't know how to define non-perturbatively 5-4 theory in fractional dimensions. But what we can do, which is not exactly the same but quite similar, is to fix the dimensions, say, to 2 or 3. And then replace the kinetic term, rather than taking a Laplacian in the kinetic term, you take a Laplacian to some power, and the power is fixed in such a way that the quartic term is weakly relevant in a renormalization group sense, to mimic the same, say, scaling behavior of the Wilson-Fisher fixed point. So this model is supposed to describe the critical behavior of long-range Ising model in d dimension, in 2 or 3 dimensions. So by long-range Ising model, I mean an Ising model in which the coupling is ferromagnetic and decays like 1 over distance to the d plus s. S is positive. Equivalently, depending on your taste, another model that is believed to be in the same universality class, so to have the same critical behavior at the critical point, is the analog of this in the Ginzburg-Landau formulation. So you can replace sigma, this Ising spin sigma, by a scalar field phi, and you define an action that is formally up to small or short distance regulators that I didn't write explicitly as a quadratic part that is the analog of this, plus a quartic self-interaction, plus a local quadratic term that with the parameter nu that should be tuned as a function of lambda, so to put the system at criticality. So somehow one has to imagine in order to be at criticality, to tune the beta in front of the h here in the Gibbs measure, or here to tune the nu to be at criticality. Yes? This is formal.
Formal is the value for lambda, the lambda?
Sorry?
The lambda It's not the critical value for small error.
The idea is that you fix lambda small, and then you fix, once you fix lambda, you choose nu as a function of lambda, so that the system is at criticality.
Criticality, you mean that?
I mean that, so I should actually introduce, say, a short distance cutoff, analog to the lattice, for instance, and then require that the large distance behavior of correlation is power law. So this can be a criterion.
But if it's not the fractional Laplacian, do you agree that the lambda is just the standard Dirichlet energy? Lambda is not normal, right?
The lambda?
Yes. It's not the value, the 543, the usual 543, the value of lambda is not normal to tune it at criticality.
You're not tuning lambda. You're tuning nu. You fix lambda small enough, and then you tune nu.
What I don't understand is that if I follow you, if I take any lambda, I tune nu, I have a CFT in the scale limit.
Yeah, which is in the at the end is expected to be independent of lambda. So the scale limit is expected to be independent of lambda and to be the same as the one here. So this is somehow the universality statement. No, not at all. This is again overview motivation. So what is believed on the basis of heuristic analysis is that so for any positive S there is a critical point and there is a scale limit, and the nature of the scale limit is different depending on the value of S. So if S is not too large, the critical behavior is expected to be the same as the reference mean field model, which is the Gaussian model in which you only retain this part here. When S is larger than d over 2 and not too large, then it's believed that the critical behavior is described by a non-Gaussian fixed point with critical exponents that are in general different from those of the reference Gaussian theory. They vary continuously with S, and if S is even larger, then one expects that the critical behavior is the same as nearest neighbor Ising in dimension D. In particular, the critical exponents are independent of S. This is the prediction of Fisher, Mein, Nickel, and of Sack in the early 70s. As I just mentioned, this complete picture is far from being proven, but there are some rigorous results. So if you take S slightly larger than d over 2, you are in a suitable sense in a perturbative regime such that the non-trivial fixed point is accessible by rigorous methods. So what you can ask, for instance, is to construct partition function and correlation function of a perturbed Gaussian theory, in which the reference Gaussian theory is a measure in which the two-point function is this regularized version of the propagator that I implicitly introduced in the previous slide. So you can, for instance, say that the two-point function is the Fourier transform of 1 over k to the d over 2 plus epsilon. This is what I refer to as fractional Laplacian in a sense, with an ultraviolet regulator. So this chi0 you can think is a smooth version of a cutoff function in k-space. So it's identically equal to 1 below 1 and say identically equal to 0 above 2, and is C infinity, whatever. So this is the reference Gaussian theory, and then you perturb it as you usually do with phi-4 theory, and then you add this this term that you want to tune in such a way that correlation functions decay power law at large distances. Okay, so the partition function and correlation function, the fixed point, have been constructed by rigorous renormalization group methods by Bridges, Smith-Hertz, Coppola, and many collaborators. The analysis is quite complicated, and one, of course, is complicated in general, but there are some technical complications that make life quite more difficult than what is really necessary. In a sense that I will try to clarify soon. So for scalar fields, as you may know, if you encountered, you studied the theories of construction of 5-form models in 2 or 3 dimensions, for instance. Then the mathematical analysis is complicated by the large field problem. So scalar fields in a functional integral like this, so one cannot naively expand e to the minus lambda phi 4 in a Taylor series, because there are situations in which phi may be very large, and these regions in which the field is very large are unlikely, but one has to sort of monitor this, the presence of this, and this complicates a lot the story. Yes?
Yeah, I have a completely naive question, sort of come out of my ignorance. So what are the signs of lambda and mu? So lambda probably has to be positive for the integrals to be convergent at all, but...
yeah, and no turns out to be what it is, which I should know, but now I don't.
But so when you say something like doing perturbative around Gaussian, you'd probably want the Gaussian to have a positive definite covariance.
Yeah, sure.
So, and is it in the formulation of, for instance, the previous slide, when you sort of said that you can analogously do a long distance Ising or this Ginsburg Landau, is nu going to be positive there as well?
I think it's not necessary for the theory to be well defined, because you have this lambda anyway. This nu will be linear in lambda, and you can compute it at lowest.
I'm trying to think of what it means. What does it mean to perturb around the Gaussian if the Gaussian had negative?
This should be thought of as being part of the perturbation.
Ah, okay. I see.
So the reference Gaussian is this one, or possibly a dressed version, but still you will keep this for reasons that I'm not sure I will be able to fully explain. But
thank you. That clarifies. Yes. Thanks.
okay. So due also to this technical complications related to the large field problem, the existence of the fixed point has been proven. Critical exponents have been computed at lowest non-trivial order, showing in particular that there are anomalous, so-called anomalous exponents. When I say anomalous exponents, I mean exponents that are different from those of the reference Gaussian theory. But actually, the results are partial, and it's hard to imagine how to check detailed properties such as CFT axioms in this setting. So a simpler but still non-trivial setting is the fermionic counterpart of this model. Somehow this is defined by a functional integral that is formally the same as the one I wrote in the previous slide, but with the field phi replaced by a Grassmann field rather than a scalar field. So a model of this sort has been proposed, or at least something very similar has been proposed by Gavesky and Kupianin in 1985. They also proved the existence of a non-trivial fixed point for this model, but they didn't investigate the structure of this fixed point further. And in the last few years, we started the project with Vieri Mastropietro and Slava Richkov, and then we involved the postdoc Giuseppe Scola, with the purpose of looking into more detailed properties of this fixed point with the midterm goal of understanding some of the CFT axioms. We are still far from it, but we certainly clarified some important details of the fixed point theory that Gavesky and Kupianin proved to exist. And I think we have a setting where many more detailed questions can be asked and possibly answered. So our results in short are the following. So we consider this fermionic version of the long-range Ising this 5-4 theory with fractional Laplacian. We compute the non-Gaussian fixed point effective potential in a more detailed way as Gavesky and Kupianin. In particular, we prove its analyticity in epsilon. This was not guaranteed a priori, so there were discussions about whether it was just Borel summable rather than analytic. And we compute the anomalous critical exponent to improve its analyticity in epsilon. This is quite peculiar also, but it's peculiar of the fermionic nature of the theory. So scalar field counterpart is expected to be at best horizontal. And in our latest work, we also define and compute the scaling operators of the fixed point theory associated with the field and density operators. We just focus on 2 scaling operators, but the procedure should work for much more general scaling operators as well. Many things remain to be done, but as I said, the setting seems to be amenable to study validity of other aspects of the CFT axioms and related issues. Okay, so let me now start to define more precisely the model. So the model I would like to focus on is the fixed point theory, but in order to define the fixed point theory, I need to tell you something about the renormalization group map. So it's not completely trivial, the definition. I may give you the definition just from scratch, but I don't think it will be very understandable. So let me try to sketch the kind of construction, RG construction, that brings us to define the fixed point theory. So let me start with a partition function that has exactly the same structure as the one above. Now I don't put the minus sign because in the fermionic case, it's not a priori the sign of lambda 0 is not necessarily positive or negative. I mean, there is no issue of stability in a fermionic setting. By fermionic here I mean that psi is an n-component Grassmann field. This is a reference Gaussian. This is a reference Gaussian integration. I mean, roughly speaking, it means that you can compute the expectations by saying, expanding this in Taylor series and term by term applying the fermionic Vic rule rather than the standard Vic rule. The 2-point function that completely defines this reference Gaussian integration has exactly the same form as the one I mentioned before. So it's the Fourier transform of 1 over k to the d over 2 plus epsilon with ultraviolet regulator that is a smooth version of the characteristic function of k smaller or equal than 1. Should be, so the effect of this is somewhat analogous to the presence of a lattice. Okay, so how do we proceed? And one could define similarly, say, generating function of correlations if one wants to compute correlation. So let me start by focusing on this. How do we compute the partition function? So the iterative procedure I alluded to when I mentioned Wilsonian renormalization group can be made more concrete in this setting as follows. So one starts by decomposing the propagator by in a multi-scale fashion. Somehow one slices momentum space in slices in which k is of order gamma to the h. Gamma is a scaling parameter, whatever you like, say 2, 4, 3, square root of 2. H is a negative index, which is the log of the momentum scale. One convenient way of slicing is to rewrite the chi, this cutoff function appearing in the propagator, in a telescopic way. So you add and subtract okay, and each slice, so you denote by FH this generic term in this telescopic sum, and this is something that is supported around gamma to the h. So once again, h is negative, so this is a small slice. Okay, and then you use the so-called addition principle for Gaussian integrals. So your original propagator with the cutoff chi less equal than -1 is rewritten as the one on scale 0 plus the one with scale smaller equal than -1. These two guys, chi g smaller or equal than 0 and g smaller or equal than -1 have a certain scaling relation, and this is the fluctuation propagator. So you, using this rewriting, you write the random field psi as a sum of two independent random fields with propagators this and this, and then you integrate out the one corresponding to the fluctuation on scale 0. So this is concretely the operation corresponding to averaging over small scale degrees of freedom. So you compute this and you re-exponentiate, and you put your partition function in a form that is reminiscent of the original one, with the cutoff now moved on a smaller scale, and the quartic potential replaced by this more complicated effective potential. If you now decide to rescale things, you bring back the system in a situation in which the reference Gaussian measure is exactly the same as before, but now the effective potential is different. So you can keep doing this. So at each step, you integrate out degrees of freedom on scale 1, 2 to the -1, 2 to the -2, etc. And you get a sequence of effective potentials. And as I told you, one can, if desired, and this is actually good to do, to rescale things, so to bring back your functional integral, your left with computing, in a form that is as close as possible to the original one. So to do that, you have to rescale. You have to use the scaling properties coming from this definition of the two-point function. You recognize that the propagator on scales below h is this rescaling of the original propagator. So inspired by this, you rescale fields, and the scaling involves this scaling dimension of the Grassmann field, which is in this case d over 4 minus epsilon over 2. This is the scaling dimension of the field. This rescaling operation defines what is called the dilatation operator. Okay, so now if you combine the dilatation operator with the effective potential, you get a rescaled effective potential, which lives somehow on the same scale, order 1, as the original Bayer potential. Yes.
So just again, a naive question out of ignorance. In principle, the new effective potential contains infinitely many terms or something, or
yes.
Yeah.
Now I will come to that. So it's not just a two-terms polynomial as the original one. It immediately has infinitely many terms. Okay, so what is called the renormalization group transformation is the appropriate combination of the dilatation operator and integration on a single scale. It turns out with this specific definition of our propagator that is independent of the scale, and it's what I call the naive Archie transformation. Naive for reasons that I will get to hopefully. Okay, so as just mentioned, the rescale potential has a structure that in general is much more complicated than the original one. So it's not just a combination of two local monomials, but it's an infinite combination of monomials of arbitrary order. So this should be interpreted as a formal series, formal in the sense that should be identified with the infinite collection of integral kernels associated with the monomials of arbitrary order. So this should be seen as a way to write an infinite vector. This infinite vector can be thought of as the element of a Banach space in a way that I will specify in a few slides. Each of these kernels is well defined, is actually an analytic function of lambda 0 and epsilon thanks to the fermionic nature of our theory. So this would not be, so this can be computed by convergent perturbative expansion thanks to the fact that we have a fermionic theory rather than a scalar field. So here is where somehow things simplify substantially compared to the scalar field case. Still things are complicated, as you see, but less complicated than the scalar field counterpart. So these kernels have a size that can be measured in terms of a weighted L1 norm. So the weighted L1 norm is something of this form. So the weight is something that is chosen so to encode the decay property, the typical decay properties of this. So one has to look into what are the typical decay properties. These are stretched exponential in our setting, so it's fine to use a weight that is which is a stretched exponential. This dx prime indicates integration over all variables but one, and this choice is somehow related to translation invariance that is valid in our setting. So you can now wonder how the iteration of the RG map affect the size of the kernels. So this is also something complicated, because you in principle you have to answer to this question. You have to compute the full map from a collection of W's to a collection of W prime, which one can do, but is not so straightforward. So in order to orient oneself, one possibility is to start looking at the effect of the dilatation operator on the kernels. Somehow the dilatation operator is exactly the action of the renormalization group map at linear order. So if you linearize, I'm slightly imprecise, but okay. So at linear order, the RG map coincides with the dilatation operator. So you can start looking at what's the effect of the linear part of the RG map, which is the dilatation operator, on the growth of these norms. So it turns out that the dilatation operator, just by rescaling, has this effect on the norm. So it's multiplied for the purpose of an upper bound by this scaling parameter gamma, say 2, to the d minus n times the scaling dimension of the field. So depending on whether this prefactor is larger or smaller than 1, this indicates that the action of the linear part of the RG map tends to increase or decrease the norm. Somehow the idea is that if this is smaller than 1, sufficiently smaller than 1, then hopefully the nonlinear effects don't change this fact. While if this is larger than 1 already at the linear level, we have no hopes. I mean, things are going to be bad. Okay, so this motivates the introduction of this terminology. So terms with scaling dimension, d minus n times the scaling dimension of psi, is positive are called relevant. These are the bad guys. Those with negative scaling dimension are irrelevant. These are the good guys. And okay, if you happen to have something in between, you call them marginal. So in our case, you can well, sit down and compute what you get. For n equal 2, the scaling dimension is d over 2 plus epsilon. For n equal 4, it's equal to 2 epsilon. And for n equals 6 and higher, it's negative for epsilon sufficiently small. So here you see the quartic term is weakly relevant. This is what I referred to earlier. It's positive, the scaling dimension, but it's order epsilon. And the quadratic term is really relevant. The fact that the quadratic term is relevant is sort of normal. The point is that this corresponds to the fact that a term like psi squared corresponds to or the prefactor in front of the psi squared correspond to a parameter that needs to be tuned in order to for the model to have good infrared properties. If you leave that parameter if you fix it randomly, the flow will just diverge. Things will go bad. But if you tune it appropriately, the tuning corresponds to fixing, say, the temperature to the critical one. Then you have hopes that things work well. Okay, so we, in any case, from this classification, it's clear that we have to do something with the quadratic and quartic terms. So what one does is to rewrite them in a suitable way. So the suitable way is to sort of rewrite them in the form of two local terms that look exactly the same as the original psi squared and psi 4 term we had in the paired action, plus terms that are written in an explicit irrelevant form. So I'm starting to be out of time, so I think I will not enter these computations. I will just mention very, very briefly. So the kind of manipulation one does when one starts with a general quadratic term is to say here add and subtract the field at location x. In this way you get one term that is local and another term that involves a difference. This difference can be written as the integral of a derivative, and so this term can be put in a form involving extra derivatives. These extra derivatives somehow improve the scaling dimension of this remainder, which is called, is written here in what I call interpolated form. So I don't want really to describe the details, but the idea is that both the quadratic terms and the quartic terms are written in a way in which we isolate a local quadratic or quartic term. These two terms have exactly the same structure as those we had originally in the bare action, plus terms that have extra derivatives that are irrelevant, have negative scaling dimension. So in this way, if we write things in this way, we can always represent the effective potential as a sum of two terms that have exactly the same structure as the original ones, plus a formal infinite series of terms that are all irrelevant. Somehow we will think the effective potential after some iteration as an infinite vector whose first two components are this mu and lambda, and all the other components are the kernels of the irrelevant things. The renormalization group map is a map from an infinite vector of this sort to an infinite vector of the same form. And this vector can be thought of as an element of a Banach space using the norms that I introduced above. So the norm of an element in the Banach space is defined by this, and so what we prove in our first theorem is that if lambda is small enough and if you fix mu 0 appropriately, then this sequence of rescaled effective potentials remains in the same Banach space at all steps, and it converges to something non-trivial. Non-trivial means that it's not, it doesn't consist just of the quadratic component, but for instance, lambda star is different from 0. So it's a potential that involves non-quadratic terms. So this is why I refer to this fixed point as to a non-Gaussian fixed point. So theorem 1, which was proved a few years ago, is that so this fixed point potential exists, is non-Gaussian, and is analytic in epsilon. So you can compute you can compute in convergent series all these guys.
Is it explicit enough?
Well, not. You don't have closed formulas. You have convergent expansions. So I have a quite explicit algorithm to compute everything. So if you ask me, it's a bit like Feynman diagrams. So I have an algorithm. You cannot use Feynman diagrams, otherwise you don't manage to prove convergence. But we have other kind of say diagrammatic expansion that allow us to compute at any specified order things. But you don't have closed formulas. Let me also stress that this non-Gaussian fixed point is attractive. So you don't need to start precisely from this. You could have started from a bare potential including irrelevant terms, you would move to the same non-Gaussian fixed point, provided you fix mu zero appropriately. So if you change the bare potential by adding irrelevant terms, you may need to change mu zero. But if you fix mu zero every time in the good way, you're attracted by the same fixed point. Okay, in particular, if you decide to start from the fixed point, then you stay on the fixed point forever. So, motivated by this, we can decide to look at the theory in which the bare potential is the fixed point potential. So this is the closest possible theory to the CFT that we would like to ideally associate with this. So we would like to. We would like to fix the potential to the fixed point potential and understand its correlation functions. So are these correlation functions scale invariant? Are they conformal invariant? What are the critical exponents? What are the scaling operators? So these are the natural questions we can ask now in this theory. That is a theory that has an ultraviolet regulator, morally something like the lattice that was considered yesterday. But now it has a bare potential, which is the fixed point one. So it has sort of invariant properties under rescaling. So there are good hopes that this is the theory that either is a CFT or is the closest possible to a CFT in the presence of this ultraviolet. Okay, so I have a few minutes. So
you know if it's going to be a CFT or not? You know if it, I mean, you're talking about
no, okay, no, I will get to.
Is it a CFT or not, or do you not know?
Okay, so okay, let me state the main results and then we will discuss. So the issue is also how we want to identify, what we want to identify the correlation functions with. Do we really want to identify correlation functions with endpoint function or to some other response function obtained as derivatives of the generating function? So this is one of the points. Of course, all is open to also to discussion because we don't have final answers yet. Okay, so what we do is in order to compute correlation functions, is to define now a theory in which the potential is the fixed point potential plus certain terms which we couple either psi or psi square or whatever observable we want to compute the correlations of with an external field. So correlation functions will be obtained by differentiating this generating function with respect to phi or j and then setting the external, the source field. So if you want to define scale invariant correlation functions, it's better actually not to look at correlation functions of psi or psi squared, but actually to correlation function of certain operators that we want to construct, the scaling operators, by the requirement that this action in the presence of external fields has this structure, but is also a solution of a fixed point equation. So somehow the requirement that H star has this structure and the solution to a fixed point equation fixes uniquely the scaling dimensions of these external fields. And these uniquely fixed critical exponents provide really the values of the scaling exponents associated to certain scaling operators. Okay, I don't want to enter really, I will try to convey the main message. So what we do is we have the same methods of theorem 1, somehow we compute compute in the sense that we provide an algorithm such that all the irrelevant terms are given by convergent series. And we do that by generalizing this, this procedure of splitting local relevant or marginal terms from the irrelevant ones. monomials. And once we do that, we can finally compute, say, the 2-point function associated with the field operator and to the density operator. So the response functions I focus on are defined this way. So once again, the procedure is that I define a functional integral in the presence of external fields, whose action is the fixed point potential constructed above, plus these couplings, plus irrelevant terms fixed in such a way that the whole thing is a fixed point potential of our renormalization group. And correlation functions are by definition given by the functional derivatives of this generating function. If we do so, what we prove is that these response functions are exactly scale invariant with explicit scaling dimension. So the scaling dimension of the associated with the field operator is the same as the mean field one. So there is no anomalous exponent associated with the field, but there is an anomalous exponent associated with the density. So if you compute the psi-squared correlations, these have a large distance decay exponent. Well, in this case, well, not large distance, just a power law behavior that is not the same that you would get in the reference Gaussian theory, but is modified by this eta2. This is a critical exponent that is analytic in epsilon. So we have, again, an algorithm providing all the corrections you like, and we prove that this algorithm gives a convergent expansion. So, okay, these response functions are not exactly 2-point function of something. They are 2-point function of something up to a stretched exponential remainder. So in this sense, so this is where I mean, I'm happy to open a discussion, not maybe now, but even in the next days. So the response functions defined as functional derivatives of our generating functions are equal to 2-point function of something plus stretched exponentially decaying term at large distance. The presence of these terms are due to the fact that we kept a finite cutoff. I don't think that there is a way to eliminate this remainder in the presence of a cutoff. So this says that the best you can do if you want to define endpoint function of something is to have an endpoint function of appropriate operators that are scale invariant up to a stretched exponential remainders. And I believe that there is no way to eliminate these remainders if you intend to keep the ultraviolet cutoff fixed. These operators are what I define to be the scaling operators in our setting, and we have a concrete procedure to compute. The scaling operator associated with psi is not psi. It's psi plus a certain kernel applied to psi cubed, plus certain kernel applied to psi to the 5, etc. So it's an infinite series, again, of monomials. The kernels of this associated with the monomials can be constructed as analytic functions by our procedure. And so we provided an explicit procedure and bounds for the scaling operators associated with psi and psi squared, but I believe that in principle this can be done with generic composite operators. But of course we are far away to construct a complete basis of scaling operators, even though I believe this is the right route. Okay. There are many things to be proven. Yeah. So okay. Let me maybe mention very vaguely some aspects of the method of proof. So the uniqueness of the fixed point is based on a contraction argument in a Banach space. The explicit construction of the fixed point uses an expansion in 3 diagrams, Gallavotti-Nicolò trees. This is absolutely convergent thanks to the Grassmann anti-commutation rules. So it would not be, the analog would not be convergent for scalar fields. The key combinatorial lemma to prove absolute convergence is due to Bridges, Battle, Feder, Bush, and Kennedy, and dates back to the second half of the 80s. The existence of the fixed point potential in theorem 1 only requires L1 weighted bounds on the kernels, while the construction of the response function and the bound on this stretched exponentially remainder associated with the definition of scaling operators requires slightly more sophisticated bounds in terms of a mixed L infinity L1. This is somehow the content of the second paper we wrote. There are many things to be proven, but once again, I believe that this setting in which, thanks to the Grassmann nature of the variables, we have access to a convergent expansion rather to an asymptotic one, which is much more difficult to control, is a good setting to try to test a number of predictions that are at the basis of CFT. We are far away from that, but I believe that questions like the construction of the 3-point function, which would be the first real understanding whether it has the same structure as predicted by CFT, would be the first big, I think, progress towards understanding conformal invariance in this setting. It is not beyond reach, and is actually the plan of my research in the coming years. And I think I'm done. Thanks.